Okay, so today we are talking about geometric sequences as exponential functions. So we're going to identify and generate geometric sequences, and we're going to relate geometric sequences to exponential functions. So you could send a chain email to a friend who forwards the email to five more people. Each of these 5 people forwards the email to 5 more people. The number of new email generated forms a geometric sequence. Okay, so the first person generates 5 emails. If each of these people sends the email to 5 more people, 25 emails are generated. If each of the 25 people sends 5 emails, 125 emails are generated. The sequence of emails generated, 1, 5, 25, 125, is an example of a geometric sequence. In a geometric sequence, the first term is non-zero, and each term after the first is found by multiplying the previous term by a non-zero constant, r, called the common ratio. The common ratio can be found by dividing any term by its previous term. So it says to determine each sequence, is it arithmetic, geometric, or neither? And then explain. So if we have 256, 128, 64, and 32, well, we can find the ratios of consecutive terms. So we would take 128 divided by 256. That would give us 1/2. Then we could take 64 over 128. That would be 1/2. And 32 over 64 would be 1/2. Since the ratios are constant, the sequence is geometric, and the common ratio is 1/2. Okay? So that is geometric. So here we have 4, 9, 12, 18. So the first thing we want to do is, again, do our ratios and see if we are consistent. So 9 over 4 would give me 2 1/4. 12 over 9 would give me 1 1/3. And 18 over 12 would give me 1 1/2. So the ratios are not constant. So that means that the sequence is not geometric. So now we have to take the difference between the two. So we say 9 minus 4 is going to give me 5. 12 minus 9 is 3. And then 18 minus 12 is 6. There is no common difference. Okay? So the sequence is not arithmetic. There has to be a common difference for it to be arithmetic. Thus, the sequence is neither geometric nor arithmetic. So if it has a constant ratios, it's geometric. If it's not geometric, then you check for arithmetic. And if it does not have a common difference, then it's neither geometric nor arithmetic. All right. So determine whether the sequence is arithmetic, geometric, or neither. So again, we can, so I would do 63 over 21. I would do 189 over 63. And I would do 567 over 189. Okay? And so 63 divided by 21 is going to give me 3. 189 divided by 63 is going to give me 3. And 567 divided by 189 is going to give me 3. So the ratios are all constant. So this would be a geometric sequence. All right. So find the next 3 terms in each geometric sequence. Okay, so they tell us a geometric sequence. We need to find the next 3 terms. So the first thing we want to do is find the common ratio, which is what they did here. -4 over 1 is -4. 16 over -4 is -4. And -64 over 16 is -4. Then we are to multiply each term by the common ratio to find the next three terms. So if my last term is negative 64, I can multiply that by the common ratio of negative 4, and that's going to give me a positive 256. Then I take that and multiply it times negative 4. That's going to give me negative 1,024. Then I multiply that times negative 4, and I'm going to get 4,096. So the next three terms would be 256, negative 1,024, and 4,096. Once the common ratio is known, more terms of the sequence can be generated. The formula can be written as A subscript n equals A subscript 1 times r to the n minus 1 power, where n is a counting number and r is the common ratio. So find the next three terms of the geometric sequence, okay? So we're going to do it just like the first one. The first thing we're going to do is find our common ratio. So I would have, so we would have 405 over 1,215. We would have negative 135 over 405. And we would have 45 over negative 135. And let's see, 405 divided by negative 1,215 is going to give me negative 1/3. 135 divided by 405 is going to give me negative 1/3. And of course, we should get all the way across because they already tell us that it's a geometric sequence. So of course, we get the same answer everywhere. So then we just take 45 in this case, and we can multiply it times negative 1/3. And that's going to give me approximately 14.85, and then actually, if I leave it as a fraction and take 45 times negative 1/3, that's going to give me 45 over 3, and 45 over 3 is going to give me a negative 15. And then if I take that negative 15, multiply that times negative 1/3, and that's going to give me a negative 15 over negative 3, which would be a positive 5. And then I would take 5 times a negative 1/3, and that's going to give me a negative 1 2/3. Okay, so my three next terms would be negative 15, 5, and negative 1 2/3. Okay? All right. So geometric sequences and functions. So finding the nth term of a geometric sequence would be tedious if we use the method above. If we do what we just did and keep multiplying by that constant ratio, what if you needed the 100th term? You would have to do that over and over and over again. So we can use that formula that I discussed, and that's what we're going to do now. So the table below shows the rule for finding the nth term of a geometric sequence. So the first position or the first term would be A subscript 1. To find the second number in the sequence, it would be A subscript 1, or the first number, times your common ratio. For the third one, you're going to A subscript 1 times R squared. Your third one, you're going to do A subscript 1 times R cubed. And you would keep going like that. So what we could say is we could say the first term, or A subscript 1, which would be the first term, times R, the common ratio, to the n minus 1. So you notice that this is 3, the exponent is 2. The fourth term, the exponent is 3. So we're just taking the term minus 1 to figure out what the exponent should be. So it says, notice that the common ratio between the term is r. The table shows that to get to the nth term, you multiply the first term by the common ratio, r, raised to the power of n minus 1. A geometric sequence can be defined by an exponential function in which n is the independent variable, a subscript n is the dependent variable, and r is the base. The domain is the counting numbers. So the nth term, a subscript n, of a geometric sequence with the first term of a subscript 1 and common ratio r is given by the following formula, where n is any positive integer and a subscript 1 and r does not equal 0. So again, here is our formula we're going to be using. All right, so let's look at that in practice. So we are to find the nth term for the sequence. So basically what they're telling you there is you need to find the equation, okay? So first thing I want to do is find my common ratio. Well, I would take 12 divided by 6, or 12 over negative 6, would give me negative 2. 24 over 12 would give me 2, and 48 over negative 24 would give me negative 2. So my common ratio is negative 2. So I start with my first term, that is negative 6. Then I times that by my common ratio, which is negative 2, and then that would be to the n minus 1 power, okay? Now with that, I can find any term in the sequence that I want. So B says find the 9th term. So the 9th term, all I would do is plug the 9 in for the n. And so I would have negative 6 times negative 2 to the 9 minus 1, or 8th power. So the first thing I'm going to do is to find the negative 2 to the 8th power, which would be 256. Then I would take negative 6 times the 256, and I end up with negative 1,536 as the 9th term of the sequence. Okay? All right. So here we are to write an equation for the nth term of the geometric sequence. So we would go 20 over 5, which is going to give me 4. Then we would have 80 over 20, which is going to give me 4, and 320 over 80, which is going to give me 4. Okay? All right, so that tells me that I have a common ratio of 4. So I would say a to the nth would equal the first term. The first term is 5, times the common ratio, which the common ratio is 4, to the nth first power, n minus 1 power. Okay? All right. So now they want to know what the 7th term of the sequence is. So the 7th term is going to be 5 times 4 to the 7 minus 1 power, or 5 times 4 to the 6th power. And then that would give me 5 times 4,096. And so the 7th term is going to be 20,480. And so you can see how these geometric sequences can go very large very quick. We started at 5, 7 numbers later, and we're at 20,480. Okay? 4 numbers later, we were only at 320. So you could see how it's going to start. It would start jumping bigger, bigger, bigger. So the formula really helps us solve these. All right. So you try this one, come back, and let's see how you did. All right, let's see how you did. So in this one, they're giving you the second term. So the first thing you have to do is find the first term. So remember, this is the formula to find the second term. So we plug 288 in equals, because we're looking for the second term, would be the first term times 1/4 the common ratio, 2 minus 1, or to the first power. Now, you would divide both sides by 1/4, but remember that's multiplying by the reciprocal. So it'd be 288 times 4, which would give me a subscript 1 of the first term as 1,152. Now I can bring it back over, and now I can look for the sixth term. So 1,152 times 1/4 to the 6 minus 1 power, or to the fifth power. That would be 1,152 times 1 over 1,024. And then you simply multiply those, and then when you divide it, you get 1.125. So the sixth term would be 1.125. All right. Lastly, there's a word problem. It says the NCAA women's basketball tournament begins with 64 teams. In each round, 1/2 of the teams are left to compete until only one team remains. Draw the graph to represent how many teams are left in each round. Well, you can compare it to the previous rounds. 1/2 of the teams remain. So that means the common ratio would be 1/2. Therefore, the geometric sequence that models the situation would be 64, 32, 16, 8, 4, 2, 1. So in the second round, 32 teams in the round. There are 16 teams to compete, and so forth. So we can use that information and plug it. So first round, 64. Second round, 32, and so forth. And that would be our graph. If you got any questions, let me know. Otherwise, have a great day.